Today we have another awesome integral that evaluates to a really beautiful result. And our set of tools today is fairly simple. All we need is Euler's formula, which states that e to the I t equals the cosine of t plus I times the sine of t. And we need the Laplace transform. Now, the Laplace transform of some function f of t is a function of the complex variable s and equals the integral from 0 to infinity of e to the negative st times f of t integration with respect to t. So let's call our integral I, and we can write our integrand, which right now is the product of an exponential and a trig function. We can write it as a purely exponential function using Euler's formula. Now we have this cosine of 2x squared term, which is the real part of the exponential function e to the I times 2x squared. So this implies that I equals the real part of the integral from negative to positive infinity of e to the negative x squared times e to the 2ix squared dx. And multiplying these two exponentials together, we get the real part of the integral from negative to positive infinity of e to the, I'm going to factor out a negative x squared, and that will give us negative x squared times 1 minus 2I as the argument of the exponential function here, and we're integrating with respect to x. Note one more thing, that we have an even function. We're integrating an even function. So instead of integrating from negative to positive infinity, we could just integrate from 0 to positive infinity and double the result. Now the structure you have here is suggestive of a Gaussian integral with a complex number t as part of the argument of the exponential function. Now, the results of the evaluation of such a case of the Gaussian integral is the same as the case where t would be a real number, and we're going to prove that. We're going to prove that using the Laplace transform. So yeah, that's a bit of the bonus of this video today. So let's define an integral function I of t as being the integral from 0 to infinity of e to the negative tx squared dx, where t is a complex number. And using the Laplace transform of I of t equals the integral from 0 to infinity of e to the negative st times I of t integration with respect to t. And you can expand this I of t term in terms of the way you defined it up here as, and now you get the integral from 0 to infinity of e to the negative st times the integral from 0 to infinity of e to the negative tx squared, and we have this integration being carried out with respect to x, and we have the outer integration being carried out with respect to t. Now notice first up that this exponential term here is independent of x, so you can just slip it inside the integration with respect to x operator. So you now have a double integral from 0 to infinity of e to the negative st times e to the negative tx squared, integration first being carried out with respect to x and then with respect to t. Now the golden question is, can we switch up the order of integration? Well, we have a continuous function of both x and t, and the structure of the integrand suggests no problems with respect to boundedness. So using Fubini's theorem, yes, we can in fact perform the switch up, and over our region we are now integrating first with respect to t and then with respect to x. Okay, fine, that was cool, but what exactly is the utility of the switch up? Well, if I enclose in curly braces this integration with respect to t, you'll immediately notice that this here is the Laplace transform of e to the negative tx squared, where x is just a constant in the t realm, right? So this implies that the Laplace transform of I of t equals the integral from 0 to infinity of the Laplace transform of e to the negative tx squared dx. And using our trusted table of Laplace transforms, this evaluates out to 1 by s minus negative x squared. Okay, cool. Which is, of course, s plus x squared. And this is quite easy to evaluate. It's an inverse tangent, right? So you have 1 by square root s times the inverse tangent of x by the square root of s, with the limits being 0 and infinity. And as x goes to positive infinity, the inverse tangent approaches pi by 2. And as x goes to 0, so does the inverse tangent. So this here, finally, is the Laplace transform of your integral function completely in terms of the complex variable s. And now you wish to recover the integral function I of t, and for that we need the inverse Laplace transform. And a bit of trickery. We're going to factorize pi as the square root of pi times the square root of pi. And we'll take one of these square root of pi's outside along with this factor of 1 by 2. And we're left with the inverse Laplace transform of the square root of pi divided by the square root of s. Now, the square root of pi, the square root of pi is the gamma function evaluated at 1/2, which is the same as the gamma function evaluated at 1/2 plus 1. And downstairs you have you have the square root of s, which is s to the negative 1/2 plus 1. Correct? It's the same thing. It's the same thing as s to the 1/2. So using our table of Laplace transforms again, we see that all of this evaluates to t to the negative 1/2. So this is the structure of your integral function I of t. And now let's take a moment to remember exactly what integral we had to evaluate. And here it is. So we're interested in the case where t equals 1 minus 2i. We only need the real part of it, and we have to double the result. Okay, cool. So I at 1 minus 2i equals the square root of pi by 2 times 1 minus 2i to the negative 1/2 according to the relation we just derived. So we can simplify the right-hand side using some beautiful complex analysis. So if z is the complex number 1 minus 2i, we can write this in in its polar form as the modulus of z times e to the I alpha, where alpha is what I'm going to call the argument. So z here equals, the modulus of z here equals 1 squared plus 2 squared, square root here, and square root 5. And you can evaluate alpha, but let's just leave it in the symbol form because we're going to need it for some trig stuff later. Now, this implies that I of 1 minus 2i equals the square root of pi by 2 times this complex number here raised to the negative 1/2. So that will give me the square root of 5 to the negative 1/2 times e to the negative I alpha by 2. And the square root of 5 to the negative 1/2, square root of 5 to the negative 1/2 would be 1 by square root of 5 to the 1/2. So this is the reciprocal of the square root of 5. Okay, cool. So let me just write all this out here. You have the reciprocal of the square root of 5. And you have this complex exponential term. But remember that we only needed the real part. So if we take the real parts and multiply by 2 straight away, So RE here to here, need to adjust the equal to sign, didn't give enough space. And okay, doesn't look too good, but you guys understand me. So yeah, so this integral here is your target integral I, and this equals the square root of pi, because the 2's cancel out, and you have the square root of the square root of 5, and the real part of this complex exponential is the cosine of alpha by 2, which can be evaluated using a half angle formula. So remember that your complex number z was 1 minus 2i. So drawing a right triangle where the base represents the real part, which is 1, and the perpendicular, if we call this angle alpha, the perpendicular represents the length of the perpendicular represents the imaginary part, which is 2, and the hypotenuse is the magnitude, is the modulus of the complex number, which is square root 5. Then we have the cosine of alpha being 1 by the square root of 5. And once you have the cosine of alpha, you can easily evaluate the cosine of alpha by 2 using the half angle formula, which is the square root of 1 plus the cosine of alpha divided by 2. Okay, so this implies that the cosine of alpha by 2 equals 1 plus the reciprocal of the square root of 5 divided by 2. And multiplying upstairs and downstairs by the square root 5 term gives us an interesting result. So you have the square root of square root 5 plus 1 divided by 2 times square root 5. And this ratio here, this one, 1 plus square root 5 by 2, is the golden ratio. So we have the square root of the square root of phi by the square root of 5. Okay, this is fascinating. So coming back to exactly what we were evaluating, this is it. So this implies that I equals square root pi divided by square root 5, and this cosine of alpha by 2 we just found out is the square root of phi, the golden ratio, divided by the square root of 5. So downstairs you have the square root of 5 squared, which will give you the square root of 5. And upstairs you have the product of the square roots of pi and phi. So all of this implies one thing. It implies that the integral from negative to positive infinity of e to the negative x squared times the cosine of 2x squared dx equals the square root of pi times phi divided by 5, which is in fact a beautiful result. So yeah, I enjoyed solving this integral, and I really hope you enjoyed the video. This is a beautiful result that deserves a like and subscribe. So thank you. See you next time.